Okay, guys, so what we're going to talk about now is Newton's laws. So everything we've covered so far has to do with motion and how we can describe motion that has a constant acceleration, right? So all those tools that we've built up for kinematics, for describing motion, those can actually describe just about any type of motion as long as we can break it up into chunks where it has constant acceleration, right? So really complicated things can be built up from those formulas. What we're going to look at now is kind of what is the driver behind this motion. So yes, we know that we can find how fast something is going if it accelerates for a certain amount of time, or how much distance it covers. Any of those things can be figured out by our kinematic formulas. But now we're going to kind of look at the forces that drive changes in motion, right? So pretty much, where does this come from? Okay, we've kind of skipped over this so far. So what we're going to talk about right now is Newton's laws, really quickly. So just kind of recapping what you guys have learned so far about Newton's laws is we just want to summarize what is going on in each of these laws. So in our first law here, I've written it kind of as its definition, and then we'll discuss it a little bit more in informal terms. So Newton's first law here, we have an object will continue its state of rest or motion, okay, unless acted on by an external force, right? So we've got this first part here, will continue its state, right? It doesn't matter if it's rest or if it's motion. Whatever it's doing, it's going to keep doing that no matter what, forever and ever, unless, okay, unless we have some external force. Okay, so what does this mean for us? That means that pretty much the universe is lazy. It wants to keep doing whatever it was doing before, right? So if something is not moving, right? For example, if we have, let's say we've got a table here, and we've got a ball sitting on the table, it will never move, right? It'll just sit there forever until somebody comes along and then messes with this ball, right? It'll just sit there forever and ever, okay? So unless some external factor comes in, nothing's going to change. Similarly, if we kind of imagine that we are out in space, okay, let's say we are on a rocket. Okay, we're going to do this here. Rocket. There's our rocket. And we're floating through space, right? So let's say the rocket is not powered, right? There's no thrusters or anything. It's just floating through space. Because we don't have any appreciable air resistance in space, there's still going to be a little bit of resistance in space. Actually, there is like a little bit of atmosphere. This will just keep going forever and ever and ever and ever, and it will never change. And it'll just keep going. The important thing here is in a straight line, right? So this, what we can call initial velocity, this will be constant. Okay, pretty much the important thing here is, if we kind of sum this up, so we've got no force, okay? This means that we have no acceleration. Okay, we can't change our velocity. If our velocity was 0, then it stays 0, right? We can call this v equals 0. And if our velocity is some constant number, it doesn't matter what that is, then it'll stay at this constant unless we have some external influence, okay? So we have this, without any force, we can't have acceleration. Now there is one important thing here that I want to outline for you guys before we move on with this idea, is that remember that for velocity, we have two parts, okay? One is magnitude, remember, because it's a vector, and the other one is direction. So what is our magnitude for velocity? This is our speed, okay? And for our direction, this is just our direction. So this means that without an external force, we can't change our speed, but we can't change our direction. That's why I say this here. It'll continue in a straight line. Later on, when we start talking about circular motion and these different kinds of forces, centripetal forces, we'll talk about how we're changing direction instead of just changing our speed. But remember that if we change either of these, this means we're accelerating, okay? If I change my speed, I'm accelerating. If I change my direction without changing my speed, I'm also accelerating, okay? So just something to keep in mind for you guys. So next, let's go and talk about the case when we do have force, okay? So if we do have an external force, then what's going to happen? Well, our second law will cover this. So just the first thing here that I want to correlate one thing really quickly, a vocabulary term that we haven't used much, and that is inertia. Okay, and our inertia is it's related to mass. It's not exactly mass, but it's related to mass. Okay, but our inertia essentially is just, it's a measure. Oops, it's a little bit messy here. So this is a measure of resistance to acceleration. How much does something resist being accelerated is our inertia, okay? So pretty much the way we're going to define this formally, right? For us, we're going to have a formula here to use this. This is going to be, if we apply a force to something, let's say this ball right here, if I apply a force to it, okay, yes, I know it'll accelerate. We kind of know this intuitively that it'll change its motion. It'll go from being stopped to moving, but exactly how much will it change that motion? That's what this formula is going to cover. We apply a force to something in some direction. Remember, our force also has a direction. We apply a force in some direction, and what's going to happen? We are going to accelerate in the same direction, okay? So these two are in the same direction. And what is it that we are going to accelerate? We're going to accelerate some mass, right? Some amount of mass is the thing that we're going to accelerate. So these three together here will build up our idea of how much something accelerates based on the force that we apply. Okay, you can see here that if I apply a lot of force, if I make my force really large, so let's go ahead and do this right here. If I have a huge force, okay, then I can have a big acceleration, right? So we have like a large number here, a large number here. Okay, this is good. Conversely here, if I have, let's say, let's say we have, some constant force, but I have a really huge, massive object that I'm trying to accelerate, even though I use, we'll call this kind of a medium force, we're going to have a very small acceleration, right? So this kind of goes on where the larger the mass that we have, the more force you need in order to accelerate it, right? So you need larger force to produce an acceleration in a larger mass. This is this idea kind of formalized in a formula here, where our inertia is correlated with our mass. The more mass we have, the more force we need in order to accelerate something. Okay? So there is actually one more thing. Our formula is not quite done. We have the basic idea here, but I need to add something in because something is missing. Okay? So in this example right here, we have a ball sitting on the table. Think about this for a moment. Is there no force on the ball? Nothing? Okay? Try to think of one force that must be on this ball at all times. Okay? I'll go and give you guys some time to think about this while I draw out this example one more time right here. So go ahead and pause the video, think about it a little bit. Is there any force on this ball? Okay, so if you guys thought gravity, there is actually a force of gravity on this ball. It's actually pulling it down at all times. Gravity always wants to bring you down to the ground, right? So there is a force on this ball. But if I look at this formula right here, why isn't it accelerating? I have a force. The ball has a mass. It should accelerate, correct? But there's something missing here. There is another force, correct? There is another force acting here, and it is the thing that is preventing this ball from just accelerating downwards into the center of the earth, right? So what is preventing that right now? What's the only thing in the way of that ball from doing that? It is, I'm going to call this the force of the table, all right? Our table force. We have a force of gravity pulling this ball down, yes, of course, but we also have this opposite force of the table, okay? And both of these together are canceling each other out. Let's say I have 1 Newton downwards, 1 Newton upwards. These two are canceling each other out so that I don't have any acceleration, okay? So to put this idea into our formula, we're going to need one more little symbol here. And that is, sorry, it's a little bit ugly, but this is a sum, the sum of all of my forces. This right here means add up all of your forces together, okay? Add up all your downward forces and your upward forces. Remember, downward forces will be negative, upward forces will be positive. Put all of those together first, okay? And whatever's left over, if one is winning over the other, okay, then you'll have acceleration. If there's something left over, if they all cancel each other out, +1 and -1, and then when we put that together, that's 0 here, then yes, my acceleration will be 0. But otherwise, if one of them is winning, then you will have acceleration. Okay, so that is the last piece here. But with only these 3 pieces of information, we can determine what the acceleration is on any object, right? So it's really handy. It's a really short, simple formula that we can use to determine the acceleration of objects. We're going to use this formula a lot, guys. So I want you guys to get comfortable with it, okay? We're going to do a few examples at the end of this to discuss how to use this formula. But before then, I just want to go over one more thing that we don't use too often, but it's a really important concept for us to know, okay? This is Newton's third law. For every action, okay, there's going to be an equal and opposite reaction, right? So this is a kind of a simple way of saying that whenever you apply a force to something, it's the same thing as that thing applying a force to you, right? So let's go ahead and draw an example here. Okay, I've got a person, and that person is going to push on a wall. Okay, so I have here force of person. And they're going to push against the wall. They're going to push here to the right. Great. They're pushing on the wall, but they're not going anywhere, correct? So just like we had in the example here, if nobody's accelerating anywhere, then there has to be an equal force from the other side, right? So I'm going to draw this here in another color, but this way I should have force of the wall, right? So here's where this comes in that there is no difference between me saying that this person is pushing on the wall or this wall is pushing on this person, even if they weren't equal, okay? Let's say the person was winning and he's pushing this wall successfully, sliding it along the ground. It's still the same thing as saying the wall is pushing on him with a certain force, okay? So whether an object is pushing on another object, it's just a matter of perspective, which one is pushing on which, but the force between them is the only thing that's actually going on. There's only one force here between them, between the two, okay, that's actually happening. So this is just interaction between forces. Okay, we'll develop this idea a little bit later on. Right now, I really want to focus with you guys on this Newton's second law right here, this idea of adding in inertia. So let's go ahead and do an example. In this example here, I have two scenarios. I want you guys to think about this, okay, before we work through them together. Okay, so in the first scenario, we have you're riding on a rocket moving at a constant speed of 4,600 meters per second. Right, that's super, super, super fast. Okay, so this is like what? Almost a 5K, so like almost 3 miles every second. Right, so super fast. So you're riding on this rocket. You're moving at an incredibly fast speed. So I want to know here, how much force are you experiencing if you're moving at a constant speed of 4,600 meters per second? Remember, we have this formula. I'll put it here on the side. Oh, you know what? Let me write it with our summation so we don't forget, since we're kind of putting this all together right now. We have the sum of all of our forces is mass times acceleration, right? So think about it for a little while. Can we calculate how much force we are experiencing? Let's say, if we want to give it, our mass is equal to 100 kilograms. Okay, so there you go. So that can be the M in F is equal to ma if you want. We've got a mass here, and we're moving at a constant speed of 4,600. So how much force do you experience? Okay. In the meantime, while you guys are working on that, I also want you to think of a very similar scenario. You are riding on the back of a turtle. Okay, poor turtle is moving. This turtle is moving at 0.01 meters per second. Okay, so this is about 1 centimeter every second. Super slow. But it does have some acceleration. It's accelerating at half let me go ahead and put this on here. I missed this. This is half a centimeter every second squared. Okay, so 0.005 meters per second squared. So it does have some acceleration, but it's moving incredibly slowly. So here, could you calculate here? You have the same mass. So we'll say also mass equals 100 kilograms. Okay, can you calculate how much force you will feel on the back of this turtle? Okay, so go ahead and try these out, these two scenarios, and then we will continue these together. Okay, so what we're going to do now is I want to work these out. So hopefully you guys were able to see kind of what I'm going for here. If I'm moving at a constant speed, okay, a constant speed, then what is my acceleration? If my speed doesn't change, remember that my acceleration is how much does my velocity change over time? Well, if this right here is 0, then my acceleration must be 0 meters per second squared, right? So when we fill out our formula right here, our force is going to be equal to our mass, 100, and then our acceleration, which is going to be 0. So the force we feel is 0, and here I'm just going to put this, our mass is kilograms, and our acceleration is meters per second squared. This is our unit right here. We're going to tie this up and give a nickname to our unit in just a little bit, but the amount of force we feel is actually 0. It doesn't matter that we're moving extremely quickly if we're not changing our speed. The speed is irrelevant, okay? So if you're thinking, well, I mean, there must be some force, right? If I stick my hand outside of a car window and it's moving at a constant speed, there's force, right? We'll get into that more later, but that actually has to do with air friction, okay? There is force pushing back. Here we're just talking about how much do you feel sitting in the car if it's moving at this constant speed, right? So, okay, let's go ahead and do this now. You guys can kind of see the pattern here. If we use this force of 100 kilograms, but now we disregard our speed and we look at our acceleration. We have an acceleration on the back of this turtle. Now we can find we actually do feel a force when we're sitting on the back of this turtle versus when we were strapped to a rocket, right? Or riding in a rocket. So here, if we calculate 100 times 0.005, we should have 0.5 kilograms times meters per second squared. Now here's the thing, this is only the second time that I have written this unit already, and we're already getting a little sick of it, right? So our units are just going to keep getting more and more complicated. So what we're going to do is we're going to start nicknaming some of these units. So we have 0.5 kilogram meters per second squared. That's a mouthful. So what we're going to do is we're going to rename this as 0.5 newtons. Okay? And this is actually just going to be abbreviated as N. Okay? So 0.5 capital N will be our unit for force, right? So whenever we're talking about force, you're going to be using newtons. Remembering our units is super important for us because it'll really help us to identify what kind of information we're being given, right? We can do this by units. So hopefully you guys were able to get a little bit more comfortable with this formula here. We're going to be using it a lot, guys. So remember, try not to mix up speed and acceleration right here. This is going to be very important for us, especially on the first exam, okay?